In Unit 2, we looked at transformations, and the first thing to look at here is symmetry. And when we talked about transformations, there were three different types of symmetry that we focused on. Point symmetry is when you turn a figure upside down and it still looks the same. That means a figure would have point symmetry. Line symmetry is if there's a line that divides a figure and has basically two mirror images. So if you folded the figure and it matches up that along a line, that means that it has line symmetry. And then rotational symmetry, it's very similar to point symmetry, but instead of having to turn the figure 180 degrees, it can be any number of degrees. And if it looks the same, then it has rotational symmetry. Notice that when we talk about rotational symmetry, we talk about rotating an object less than 360 degrees, because if you turn any object 360 degrees, it'll just get back to the original. So when we say rotational symmetry, we really mean bigger than rotating it 0 degrees, because that wouldn't change it, and less than rotating it 360. So basically a square, if I have a square and I rotate it 90 degrees, this would go back onto itself, because when you turn it 90 degrees, these are all right angles, it would completely turn on its side and look like the original figure. So this would have rotational symmetry of 90 degrees. Looking at the next vocab word here is isometry. Isometry is whenever you have some type of transformation where the lengths and the distances stay the same, so it preserves length and distances. So that's an important word to know and understand. And then there were two types of isometries, opposite and direct. So when we talk about opposite versus direct, we're talking about the orientation of the letters. So this is where we put the arrows on, and if they're in the opposite direction of each other, it's opposite. If they were in the same direction, then it would be direct. Opposite isometries are just reflections. That's when you're going to get opposite. Otherwise, rotations and translations, you'll have direct isometries. And then this is the big category here. So transformations is the big picture, and then each one of these things is a transformation. So we had translations where you're sliding an object, so you're either moving right and left, up and down, or you're adding this A value to the X's and then adding B to the Y's. Then we had dilations. We didn't do a whole lot with dilations yet, just because dilations actually aren't rigid motions, where a translation, a rotation, and a reflection, these things are also rigid motions. So we talked a lot about rigid motions and how rigid motions create congruent figures or preserve lengths and size and angle measures. So we created congruent figures using translations, rotations, and reflections. A dilation, however, is not a rigid motion because you're multiplying by some scale factor, so a dilation creates a smaller or bigger image. Then we looked at rotations, and for this, remember, you always are going to turn your paper. So when it's on a coordinate plane, we're always going to rotate our paper the opposite direction in comparison to the way we want our figure to move. So if we want to rotate our figure counterclockwise, we rotate our paper clockwise. And most often you're going to see positive angles for rotation. And remember, positive angle means the figure is going counterclockwise, so the paper goes clockwise. So they're always opposite. And then we also talked about in plane space rotations, how to come up with the center of rotation and how to find the degree of rotation or the angle of rotation. We talked about reflections. Whenever you reflect in a coordinate plane, you just have to figure out, well, however far I need to go to get to the line of reflection, that's how far your image needs to be from that line. Because remember, the line of reflection is always right in between the pre-image and the image. So it's really, if you look here in plane space, the line of reflection is the perpendicular bisector of any 2 points. And then the last thing we looked at was composition of transformations. And this is like when you have a rotation of 90 degrees of a reflection of the x-axis. You always do these backwards. So you start on the right side, you do that first, and then this one would be second, the one on the left side. And one important thing is whatever you get out from the first one, you use those coordinates to do the second one. So let's look at some examples. So for this first example, we have a translation, and it's moving P to P prime. So it's sliding this point P from 3, 5 onto 6, 1. And we want to know what are the coordinates of the image of point -3, -5 under the same translation. So the first thing is we have to figure out, well, what's the translation rule? So basically, how did I go from P to P prime? So we know that translations are always adding or subtracting values from the x and y coordinates. So in order to go from 3 to 6, I had to add 3 to the x, which really means I moved right 3. So this is going to be plus 3. And then to get from 5 to 1, I had to subtract 4, which really means on a graph, I'm moving down 4. So this is the translation rule that this first pre-image and image point used. And the question asks you to find the image of this point here. So now we're starting with -3, -5, and we want to apply this rule to it. So all that means is, starting with this point, I'm going to add 3 to x, and I'm going to subtract 4 from y, so we get 0, and then -9. So choice 1 would be our answers. Now you could do this on a graph as well. You could figure out, okay, how did I move right and left, up and down, and then just apply that, plot this new point, move right 3, down 4. So looking at this next example, for this one here, what we wanted to do is we're given some point. So I'm going to go ahead and I'm going to plot that point. So -2, 1, 2, 3. I'm labeling that point. And we want to find the coordinates of the image under this composition. So what that means, the first thing I have to do here is I have to do this reflection. So I'm doing, remember, lowercase r means a reflection, and you can always know that because the subscript is always going to be a line. We always reflect over lines, and we rotate around points at a certain number of degree. So because this is a reflection over the x-axis, and that means I'm going to look at, okay, well, here's the x-axis. I know the distance from this pre-image point to the line of reflection has to be the same as the distance from this line of reflection to the image point, because a line of reflection is what creates the symmetry. So basically, the easiest way to do this is start at A and figure out, well, how far did you have to travel? I had to travel 1, 2, 3 units, so I have to travel 3 more. So 1, 2, 3. So that would get me A prime. So my first thing that I did here was a reflection over the x-axis, and I got A prime as -2, -3. Now, some of you might remember the rule. Essentially, since I'm moving this over the x-axis, all I really did was negated the y value. So that's the rule. So you didn't have to do this on a graph, but on a graph, you count. Otherwise, you remember the rule, you negate y. You always negate the opposite. So if you're reflecting over the x-axis, negate y. Reflecting over the y-axis, negate x. So then the next thing is to do this rotation. So this is the second thing. And you need to use A prime to do this. You always use the primes to do the second one, because what this really says is a rotation of 270 of the reflection. So whatever you get out, now you're going to rotate. So this is where we're going to actually turn our paper. So since this is a positive 270, that means I need to move 3 quadrants. So I'm starting here, and I'm going to move this counterclockwise. So it's going to go 1, 2, 3 quadrants counterclockwise, which means my paper is going to go clockwise. So we're going to go ahead and we're going to turn our paper 3 times. So our paper goes clockwise. So we have 1 time for 90, 2 times for 180, and 3 times for 270. And then what I'm going to do is I'm going to replot this original. So my original here is really A prime because this was a composition. So I'm going to, let me just write my steps here. So for the rotation of 270, I'm going to, I turn the paper 3 times for 270 to the right, basically taking the top of my paper and turning it to the right or clockwise direction. And then what I do is I replot A prime, -2, -3. So I look at this picture, and this is my new x-axis, this is my new y-axis, and I go to -2, so -2, and down to -3, so 1, 2, 3. So I just pretend that this is my new graph, and I'm going to call that A double prime, and then we're going to turn our paper back. So turn the paper back. And remember, we predicted that A prime should move 3 quadrants counterclockwise, which it did. So A double prime ended up over here. So that means my A double prime coordinates, or my answer to the actual question, is going to be, now I go back and I actually read this as this was my original x-axis, this was my original y. So it's 1, 2, 3, so -3 up 2. So that's it. So that would be your final answer. So let's look at one more of these on a coordinate plane. So here we start with a triangle, RST, and we want to figure out the image after this composition. So let's start by plotting the triangle. So we have -6, 5. So I'm going to go ahead and put a scale on here. So I'm going to just do 5s all the way around. 1, 2, 3, 4, 5. And notice that it does say that the use of the grid's optional, but if you don't use the grid, then you have to memorize all those rules. So that's why I like using the graph. So let's go ahead and plot our triangle. So we have -6, 5. -7, -2, and 1, 4. And when we look at this composition, the first thing is we are doing a reflection over the line y equals x. So this one, if you're going to remember one rule, this is the rule I would tell you to remember, because this is probably the most difficult one that you actually have to do on your own. So if you're going to remember a rule, this is the one to remember. All you need to remember is that you're going to switch the x and the y values. So basically, if I'm looking at r prime, s prime, t prime, all I do is I flip each of those. So the original r becomes 5, -6. The original s becomes -2, -7. And then we have 4, 1. Now, on a graph, the line y equals x is where you would start, and that's the line that goes through the origin from corner to corner as long as you have a square graph. And this line, so let me just label it here, y equals x, what I'm going to do is I'm going to still follow that same process where the reflected figure, so this triangle needs to come up over this line and go to the other side so that it's the same distance away. But since this is diagonal, now what I do is I count diagonal distances. So if you look, I start here and I'm going to go 1½ diagonals, which just means I need to go a half and another 1. So it's basically I traveled 1½ diagonals. So the distance is the same to get t prime. And if you look, that coordinate is 4, 1, which is what I came up with over here. So to start at r, 1, 2, 3, 4, 5½ So we're going to do a half, 1, 2, 3, 4, 5. And that'll get you r prime, which if you look is the coordinate 5, -6, so that checks out. And then s, we go 1, 2½, so then a half, 1, 2, and that'll get me s prime. So then if you connect these, that gets you your set of coordinates, which we matched. So remember, this one should have been -2, -7, which that matched. So now we got to do the translation. And for the translation part, remember, you're using the primes. And it's up to you how you want to do the translation, because when you do the translation, if you want to think of it as subtract 2 from x's and add 3 to the y's, you can do that, or you can take your primes and basically move everything down 2, or left 2 and then up 3. So it's always right and left first and then up or down. So you're going to go left 2, up 1, 2, 3. And that'll be T double prime. Then I start 1, 2, up 1, 2, 3. And then 1, 2, up 1, 2, 3. So then basically from here, you just have to copy these coordinates down and you're all done. So let me do these in the same order. So R, S, T. So R double prime is at the coordinate 3, -3. Which if you look up here, I should be subtracting 2 from x, which I did. 5 minus 2 gave me 3. -6 plus 3 gave me -3. S double prime is at -4, 1, 2, 3, 4. So -4, -4. And again, check it. -2 minus 2 gives me -4. -7 plus 3 gives me -4. And then the last one is T. We got 2, 4. And then again, if you go from here, subtract 2, you get 2. Add 3 to the 1, you get 4. So there's your coordinates. So a couple other different types of examples that you might see. So for this example, the vertices of a parallelogram ABCD are these points. If ABCD is reflected over the x-axis, how many points remain invariant? So what that means is how many points remain the same. So remain the same. Invariant means like not varying. So remains the same. So the best way to do this is actually just to kind of sketch it. So if you look, we have 2, 0 is A. We have 0, -3 is B. The picture doesn't have to be perfect, but you at least want to have a rough idea. C, we have 3, -3. And D, we have 1, 2, 3, 4, 5, 0. So we have this. So now if I imagine reflecting this over the x-axis, B is going to come up here, and C will come up 1, 2, 3. So 1, 2, 3, it'll be up here. And A and D, though, are going to stay basically on the line because they don't have to travel anywhere. So here would be your new parallelogram. So basically, how many points remain invariant? Well, how many points stayed the same? There are 2. There's a point here and there's a point here. On this next example, which expression best describes the transformation shown in the diagram below? Well, let's look. This is talking about orientation. So that means where you draw on the arrows and you decide did they stay the same or did they change. So I always just go in alphabetical order. Make sure you stay in the same order. So if you look, these arrows are going to the right, where these arrows are going to the left. So the orientation changed. So it can't be choice 1 or choice 3. So it's got to be an opposite orientation. And if you look, basically to go from triangle ABC to the prime triangle, I had to flip it. So this was a reflection. I know that translations can never be opposite isometry or opposite orientation. So right away, I looked at number 4 and knew that wouldn't work either. So one more example here. If I have this rectangle and I reflect it across the x-axis. So let's go ahead and actually do that because it'll be a lot easier to answer the questions if you actually are looking at the new picture. So reflecting across the x-axis, so count 1, 2, 3, go 1, 2, 3. That'll get you A prime. Then from B, this was 8 units down, so I have to go 8 more units. C is up here at 10, so I just go 10 units down. And D is at 5 units to get to the x-axis, so travel 5 more units. So here's your new rectangle. So now we can go through and answer these questions. So it's asking you which will not be preserved. So if you look, the slope of AB is some kind of positive number, where once I reflected it, now it's a slope going downhill. So I went from a positive slope to a negative slope. So right away, that has to be the answer. The slope changed. Where parallelism just means, if you look, AB and CD, those are parallel right now because they're opposite sides in a rectangle. If you look at the new one, they still stayed parallel. Even though they were both negative slopes, they're going to be the same slope. The length of AB. Remember that reflections preserve length. So the length is going to be the same. So that didn't change. And then the measure, reflections also preserve angle measures. So these angles would have to stay the same. So that's the only thing that's going to change is the slope because of the orientation changing. The last thing then for the transformations unit is when we did some constructions in plane space. So the first thing here that we need to look at is if I want to construct the line of reflection. So think about what that looks like in your head. If I had to construct a line of reflection for this pre-image and image, basically that means the line needs to go in the middle or equidistant from each set of coordinates because it has to basically create the symmetry between these two figures. So it has to be the same distance away from each pre-image and image point. So what you do is you start with, so I'm just going to start with a line. So let's say I start and I look from A to A prime. What I need to do is I actually need to create the set of points that's equidistant from A and A prime, which is always going to be the perpendicular bisector. So you don't really need to draw in this segment, but this segment is just there because actually what I'm doing is I'm going to bisect this segment. So I'm going to take my compass and I'm going to go to point A, and remember you're going to go more than halfway, so you're going to adjust this so it's more than halfway. And then you're going to go ahead and you're going to mark an arc above and below. Not quite all that way, just basically you just need an arc above and below. And then you're going to go to the other endpoint and you're going to mark that same distance because you're going equidistant from each endpoint. And then what you do is you take your straight edge, you connect through those two intersection points because those represent where you are equidistant from both of these points at the same time, and that line is going to be the line of reflection. So this line here is the line of reflection. So you can put arrows on it, you can keep it as a segment, it doesn't really matter. But it is the line that is halfway between every point. So the last example then is, well, whenever you have a rotation, so these two figures have been rotated and you want to find the center of rotation. So again, the center of rotation always has to be equidistant from every pair of points. So what you're going to do is you're going to start off with being equidistant from one pair of points. So if I want to find equidistant from this pair of points, I'm going to construct the perpendicular bisector. So I'm going to start the exact same way, more than halfway. And you're going to do an arc above and an arc below. And then you're going to go over to the other endpoint. And you're going to keep that distance, do an arc above and below. And then I'm going to go ahead and connect those. I'm going to connect these using a dotted line just so that in the end it's actually going to be any point on this line is just equidistant from A and A prime. I need to be equidistant from every set of points. So the last example I kept, and I was done with just a line, the perpendicular bisector, because that is the line of reflection. If I would have constructed the perpendicular bisector between any set of points, they would all give me the same perpendicular bisector. So equidistant from E and E prime and D prime is going to be the same line of reflection, the same perpendicular bisector. But for rotations, you're trying to find the center, so you're trying to find a point. So I know that the point has to be somewhere on this line, I just don't know where on this line. So what that means is I need to construct another perpendicular bisector. So what I'm going to do is I'm going to pick another set of coordinates. So let's say I pick B to B prime, a pre-image and an image. What I'm going to do is I'm going to take my compass and I'm going to go more than halfway again. So I'm going to start here and I'm going to take this and expand it more than halfway. And I'm going to do an arc above and below. And I'm going to do the perpendicular bisector construction again. So I'm going to move it over here. And you don't need to make this big circle. I really just need just enough to be able to see my intersection points. So then once I get that, I can connect. So if I connect these two intersection points, now you can see where my two lines cross, or where my two perpendicular bisectors cross. That represents the point that's equidistant. So this point here represents the point that's equidistant from A and A prime, as well as B and B prime. So it would also be true if I connected any other set of points, the intersection of my perpendicular bisectors would occur at this point. So what that means is this point is the center of rotation. So then if you wanted to figure out the angle of rotation, you would connect this angle here from any pre-image to any image point from the center, and that would tell you how I went from A to A prime, what I had to rotate by to get from A to A prime. So you could actually measure that with a protractor. I'm not going to worry about doing that, but you could. And keep in mind, this is going to be a negative angle because it's a clockwise measurement.